All right, let's have a talk about concavity. Okay. Second derivative, because as with any derivative, measures the rate and the change. Now, we know the first derivative measures the rate and the change of the y value with respect to x, and we called that slope. So therefore, the second derivative measures the rate of change in the first derivative, or how the slope changes. That's what we call concavity. Now, if that second derivative is always positive, then we know the curve is concave up. Because what we're saying is the rate of change of the first derivative is positive. In other words, the slope is becoming bigger or more positive. So if you think of something that's concave up, like our standard parabola over there, y equals x squared, it starts with a very negative slope, close to negative infinity, I suppose, if we were to go all the way out there. But as we move from left to right, it's getting more positive. So it's increasing in value, the slope. We don't really need to know the actual number to know that it's concave up. We just need to know it's positive. If we know it's positive, then we know that slope must be increasing in value. That's all we really need to know. And so if it's negative, consequently, we must have concave down, because the slope, as we move from left to right, will be getting more negative. When it's equal to 0, it's possibly a point of inflection. Doesn't necessarily mean that it is, but it's a possibility. It's the first condition of a point of inflection, and we'll look at those in more detail later. Okay, so this time we're going to draw a sketch, but using the second derivative as a guide. Remember, before we just used the first derivative as a guide. But if the only tool we had was the second derivative, how could we draw a rough sketch? So let's find our two derivatives. There's my first one. My second one is 6x plus 10. If all I'm really concerned about is the sign, what I want to know is when is this going to be positive, when is this going to be negative. So I know it's going to be concave up when it's positive. So solving that simple little inequality, I know, all right, for x values greater than minus 5 on 3, the curve is going to be concave up. And so logically, if it's less than minus 5 on 3, it must be concave down. So I can draw a very rough sketch. Well, there's minus 5 on 3. And as I say, an extremely rough sketch, but I know on the right-hand side of minus 5 on 3, the curve's concave up. On the left-hand side, it's concave down. Okay. Where this is useful then is to find those turning points. But you remember how we drew up a table of values before? This saves doing that, if it's easy enough to find the derivative. So we know all of our turning points must be, first of all, a stationary point. So the first condition then is the first derivative is equal to 0. But then we can combine that with the idea of concavity to classify the turning point. Because if it's stationary and it's concave up, then it must be a minimum turning point. If it's stationary and concave down, it must be a maximum turning point. So minimum turning point if it's concave up, maximum turning point if it's concave down. So looking at this particular cubic, let's find the tools we're going to use. We're going to use both the first derivative and the second derivative in this case. So first of all, we're going to locate our possible turning points. And we know stationary points occur when the derivative equals 0. Again, remember, with your setting out, explain what you're doing. Don't just find numbers randomly. We should be able to read through your solution and follow exactly what you're doing. So I'm looking for stationary points. That's why I'm making the derivative equal to 0. Solve that equation, little quadratic, factorises nicely. I get a third and minus 1. Okay, so at minus 1, if I now sub that into the second derivative, so instead of using the table of values, all I've got to now do is work out its concavity. Concavity is negative 4. All we're really concerned about is whether it's positive or negative. That's less than 0. So I know I have a concave down parabola, and therefore, up the top. So it must be our maximum turning point. And subbing back into the y equation, you get the y value, of course. So minus 1, 2 is a maximum turning point. Now let's have a look at a third. Sub that one in, I actually get positive 4, but positive is the main thing. This one's concave up, stationary. I'm down the bottom this time. So therefore, 22 on 7 is the y value for this one, and that would be a minimum turning point. So that can save us a lot of time. If, of course, the derivative is going to be difficult to find, then I'd still go and just use the table of values with the first derivative. It's whatever's going to save me the most amount of time. Blank. Inflection points with a CT. Point of inflection. To reflect is to bounce straight back. So if you like, our parabola y equals x squared, whilst we call it a turning point, we could also call it a point of reflection, where it goes straight the other way, as opposed to our cubic, where instead of bouncing straight back, it actually twists or inflects. And so we call that a point of inflection. But basically, wherever it changes concavity, that's a point of inflection. So the first thing we need to do is to locate possible ones. Now that's going to be where the second derivative is equal to 0. Because what we're saying is there's no value to concavity there. So in order to change concavity, you must have 0. You can't change concavity, go from a negative concavity to a positive concavity without going through 0 in the middle. Yeah? So we need to check either side of the point, like we did with the first derivative, to find the concavity. So we're going to find inflection points of this particular curve. I know it must have a point of inflection, by the way, because it's a polynomial, it's continuous, and it's a cubic. And it's a cubic where there's going to be 2 turning points. So by definition, there must be a change in concavity in there somewhere. But let's locate it. So my second derivative is 24x plus 12. Possible points of inflection is when the second derivative is equal to 0. So in this case, there's one possibility. Now, as I say, logically I know it must be a point of inflection because this curve is continuous. But just logically is not good enough for a proof. We need to actually prove it. So I'm going to test it with a table of values. So in the middle I have negative 1/2. At negative 1/2 it has no concavity. So just like we did with the first derivative test, we're now doing it with the second derivative. I need to pick a point on the left-hand side of minus 1/2 and a point on the right-hand side. Let's see what concavity is doing. On the left-hand side, I'll choose negative 1. Sub that in, we get negative 12. So it's concave down at that point. On the right-hand side, I'll choose the point 0. It's always easy to substitute in. I get positive 12. So it's concave up. So yes, there is a change in concavity. And that's the key statement there. In your solution, they want to see that you understand that point of inflection means changing concavity. So you're coming up with this conclusion that yes, there is a change in concavity. So therefore, that is a point of inflection. These special ones we were talking about, horizontal point of inflection. So that's when the first derivative is also equal to 0. So it's a point of inflection where we have a horizontal tangent. Not all points of inflection do. In fact, most of them don't. The cubic is the classic example where it does there, y equals x cubed. But if you think of y equals tan x, your tan curve, it also has a point of inflection at 0, 0, but it actually comes through at 45 degrees. So the tangent wouldn't be horizontal. So that would just be a point of inflection, not a horizontal point of inflection. So if you want to prove horizontal, you also need to confirm that the first derivative is equal to 0. First derivative is equal to 0, second derivative is equal to 0, third derivative is not equal to 0. What's he talking about? Let me explain this. Here's an alternative way of finding inflection points, not in the actual syllabus. So if you do choose to use this method, make sure you explain yourself very clearly what you're doing. Okay, we locate our possible point of inflection. Second derivative is equal to 0. This is the actual theorem for it. If the first non-zero derivative is of odd order, so the third derivative, the fifth derivative, the seventh derivative, etc., then it is a point of inflection. Now, the vast number of examples we see in this course, it turns out the third derivative is not equal to 0, and you can stop there. But theoretically, it's if it's odd. So back to that one you were talking about, y equals x to the power of 4. Okay? If you think about y equals x to the power of 4, comes down, it'll be a bit flatter, and so on. So we know at naught noughts, we have a turning point. But if you go through your derivatives, first derivative is 4x cubed, second derivative is 12x squared. So sure enough, second derivative is actually 0 at the point 0, 0. So you'd think, oh, possible point of inflection, if I didn't know what that curve looks like. So I go, all right. Now if I go use my third derivative, then I'd have 24x, and it's equal to 0. The key is it has to be not equal to 0. The first time, so if I now find the fourth derivative, it's 24 and that's not equal to 0. So it's actually an even derivative. What we're saying is if the first time the derivative is not 0, is of odd order, it'll be a point of inflection. In that case, y equals x to the 4. The first time it was not 0 was an even derivative. So therefore, it's not a point of inflection, it's a turning point. Okay? So if it's of even order, like the one we just saw there, it won't be a point of inflection, and what we're probably looking at is a turning point. So the example we just did, I'd just go a step further and say, oh, well, the third derivative is 24. Remember, we've already found the possible turning point, inflection point. And I'd say, well, 24, that's not equal to 0. So the first time it's not equal to 0 is when it's of odd order, so that is an inflection point. So again, that's a key statement. So I still write that down. So yep, I've got a change in concavity. And the reason I know there's a change in concavity, third derivative measures the change in concavity. It has a value of 24. So therefore it has a change. If it was equal to 0, we'd be saying there's no change in concavity, so it's not an inflection point. So minus half 3. So the key things, if you are going to use the third derivative idea, is to, when you put the third derivative in, highlight, yes, it's not equal to 0 at that particular point. In this case, it was a constant, so it was easy. Some you might have to substitute in the x value. And go, okay, well, therefore there is a change in concavity, so it is a point of inflection if you choose to use that particular method. As I say, not actually in the syllabus. They are expecting you to use the table of values. But just like with the using either side of the first derivative, if the derivative is easy to find, then this will become quicker. If the derivative is hard to find, then okay, again, I'll just use the table of values rather than doing the extra work. Okay, let's say we go some out of 10E.